free. Okay. So, but before we go there, the topic which I am going to discuss is this. Maybe some of you have heard of it. सुना है इसके बारे में? क्या सुना? What is plasticity? कैसे होता है plasticity? हाँ, how does it permanently deform? हाँ, but how? What happens inside? Not why, how? क्या ग्रेड आया था MM302 में? फिर तो बनता है, तुम बताओ। वॉइड तो डैमेज हो गया। प्लास्टिसिटी वही है। डिफॉर्मेशन कैसे होता है? फोर्स कंप्रेशन। कैसे, क्यों बताएंगे कैसे होता है, क्या होता है मटेरियल के अंदर? बताओ, देवोपम बताओ। तुम देवोपम नहीं हो? तुम कौन हो? हाँ, अविरल बताओ। You look like देवोपम a little bit. Deformed देवोपम। हाँ? इधर बैठो, इधर खाली है, उधर वो नहीं, तुम उसका पेन ले लो, इधर बैठो। नहीं, इधर बैठो। हाँ, बोलो। कैसे होता है प्लास्टिक डिफॉर्मेशन? कृतिक ना? हाँ, बताओ कैसे होता है? तुम राशिल दोनों एक ही जैसे दिखते हो मेरे को, तो इसलिए कंफ्यूज हो जाता हूँ। और अविरल और देवोपम एक ही जैसे दिखते हैं। बोलो, कैसे होता है प्लास्टिक डिफॉर्मेशन? अरे डिफॉर्म हो जाता तो तय बात है, वो कैसे रहा वो बताओ। क्या हो रहा है मटेरियल के अंदर? तुम लोग पूरे बैच पे किसी को पास नहीं है। तुम बताओ हिमांशु, कैसे होता है प्लास्टिक डिफॉर्मेशन? तुम्हारा भी अलग से रहा।
डिसलोकेशंस ब्लॉक हो जाती है।
पहले चलेंगे तब ना ब्लॉक होंगे। ब्लॉक होंगे तो स्ट्रेन हार्डनिंग होगी, है ना? पहले चलना शुरू करें, तो चलना शुरू करेंगे तो परमानेंट डिफॉर्मेशन होगा।
अच्छा, मतलब जब उनको डिफॉर्म करते हैं तो वो जो स्ट्रेन हार्डनिंग हो जाती है, उसके
स्ट्रेन हार्डनिंग बाद में होगी, पहले तो यील्डिंग होने दो। तो यील्ड पॉइंट क्या आता है बताओ विपिन, क्या था यील्ड पॉइंट? अच्छा, तो वहीं तो घूम फिर क्या आ रहा है कि प्लास्टिक डिफॉर्मेशन कैसे स्टार्ट होता है? बताओ, तुम बताओ। नहीं, किसी को पास होना चाहिए था MM302 में, मुझे तो नहीं लगता है। So the things, the objects which we are simulating, so far we have discussed what? We have discussed elasticity, right? So the D matrix which we form, so initially we are beginning with, so we will have some values of the degrees of freedom, which in this case is displacement. In Dr. Prince's case, instead of, so you are not going through theory, huh? You're going through some theory in MM311 also.
Yes sir.
क्या पढ़ finite volume method?
अभी
fluid dynamics.
अभी fluid dynamics चल रहा है.
Little bit, huh? When not somebody to put.
हाँ.
So in finite volume you will have a cell. In finite element you have an element. So in finite volume you have to make some other, so flow consistency you have to make. जितना आ रहा है उतना जाएगा. Right? So in this case you have displacements, so n number of nodes you will have depending on what dimension it is. 2 dimensions, so you will have u1 v1 and all. 3 dimension you will have u v w and so on. Okay, so displacement is a vector. Sometimes you can also have a degree of freedom which is a scalar quantity, for example temperature, pressure. Those things also can be interpolated and solved for. So for that you will not have equation like minimization of potential energy. In that case, you will have heat transfer equation, which will be solved for. Okay. So, but basically, you will have a degree of freedom, and then you will have to solve. So, you will have a column matrix of force also. Okay. And then you will have a stiffness matrix, and then you will be solving this equation, where K is the global stiffness matrix. How do we form global stiffness matrix? That we have discussed for quadrilateral elements and triangular elements. So तुम नहीं, तुमको especially अलग से पूछूंगा. Okay. So once we have, and how are we solving this? We are solving by finding out K values, and K is described for each element. Okay, we have some Gauss quadrature, so numerical integration, and V transpose D, and then you have D epsilon and D eta. Okay, so everything so far is linear. Okay, so the D matrix is coming from elastic deformation. You have elastic modulus and Poisson's ratio, heat transfer and that's it. But after some amount of stress, so if you are applying force or if you are applying displacement, in both cases there will be initially elastic deformation and then there will be plastic deformation. Once plastic deformation begins, you will have to change the D matrix. Okay, so you will not have only elastic deformation, but you will have a significant change in the slope. And how do you take care of plastic deformation in this numerical scheme of finite element method? How do we do that? So we do that by iterations. Okay. So suppose this is force and this is displacement, and the real behavior is something like this. Okay. So from the initial point, you apply, let us say, a force of P. Okay. And then for this P, you have to calculate what is the value of displacement. Okay. And for that, you will be taking a tangent here. That will be the slope. And you are approximating the slope by taking the tangent at that point. Okay. So you will have, for amount of delta U, you are approximating a stiffness value, and that will be equal, must be equal to the force by which you are increasing. Okay. So here we are going from 0 to P, so our delta P is P. Okay. And for the real curve, if we apply delta P, then it is dropping to this point. With the initial tangent approximation, when we apply P, then we get a displacement value which is this. So we basically must have been here somewhere. So we must have got this value which is the correct value. Okay. But we are getting something else. So let us say T1. Okay, so we have an error there. Right? Is it okay? So delta U in the first iteration is KT naught inverse delta P. And the new displacement, which is this UT1, is whatever value you had previously, which was 0, plus delta U. Okay? So U naught plus KT naught inverse delta P. this is your this displacement. So now you have come from this point to this point, and you have to go to that point here. So now what will you do? Now you will take another tangent, another approximation, and this tangent approximation is not based on this point but based on this point. Do you understand? Okay. So now you take another approximation which is T1.
सर हम इनिशियल से स्टार्ट कर रहे हैं ना
Initial से start कर रहे हैं.
सर यू नॉट क्या है
U naught 0 है in this case. I have written. So this will be 0. So you will have this. But this is general, so you can start from any point. You will follow the same algorithm. Okay. So then you take another stiffness. Might not fall at the same point again. You will have again another increment in displacement. Then you will arrive at another point, and slowly, silently, like a turtle, you will reach to your destination by minimizing the difference between the approximation. Okay. So this is not needed when you don't have non-linearity. When the curve is linear, then the tangent will fall on that, and you are not going to go away from the solution. Right? This will happen when you have non-linearity in the solution. Okay? So you can have non-linearity because of three things. One is because of material. Second thing can happen because of geometrical nonlinearity. And you can have because of contact. So material nonlinearity will come because of plasticity. Geometrical nonlinearity can come because of higher order of terms in the strain. So if you have very large deformation, then you will have strains including the higher order terms, except so you have this. Plus you will have double derivative and higher order of that. So those terms will also be not significantly smaller. So for example, in case of polymers or in case of certain scenarios, also in metallic materials, when you know that there is going to be finite amount of strain, so small strain approximation is not good enough. So in that case, you will have geometrical nonlinearity. And so the deformed shape of the body will tell or might change the direction of forces. Okay, so in that case, you need to follow the non-linear curve which is appearing because of the geometry. And third thing can happen because of contacts, when you have friction, when you are modeling two bodies. And then, so for example, you are modeling an axisymmetric wall which is trying to deform a disc. So this is like a hardness test. I'm just modeling the axisymmetric part. I'm just drawing the axisymmetric part. So this is a disc and this is a ball or an indenter. Okay. So when you model this, you can make the ball rigid, you can make this and assign a material property of steel or any other material. But then you will be applying a displacement on this body so that it goes down, and you will fix not the whole part, but maybe this part. Okay? If it is hardness test, then you will fix the whole thing. And if you are simulating deep drawing, punching, then you will not fix the whole thing, only a part of that. And then this indenter will hit it and it will deform, so it will look like this. But not really, unless you define the contact. If you don't define the contact, the equations will not feel each other. So there will be two bodies transparent to each other, and the ball will be simply going without feeling the test, and you will have no results. So then you need to, so you will have nodes here, and you will have nodes here because you have elements, and then you have to assign certain equations that when these nodes come in the vicinity of this node in certain distance, then they should feel a force, a contact force, and their displacement must be derived by those contact forces. In such cases, you will have a non-linear equation to solve, which will be coming from contact equation. Okay. So in all those cases, this kind of algorithm will apply. Okay. So this is what is this? Is this familiar? Is this approach familiar? Have you seen it, heard it before? An approximation based on tangent. What is it?
Sir,
Einstein-Bohr equation. You are not supposed to answer.
okay.
Are you saying something? Is there something wrong?
No, sir.
You are trying to answer?
Yes, sir.
You can answer later, and you can answer because I don't think they will answer. So tell me what it is. सुना नहीं है? Tangent क्या है? क्या नाम है उसका? हाँ? Himanshu Vaibhavi equation. What is it? Einstein-Bohr equation. बोलो, Saurabh.
Sir, I was about to ask something. So.
Oh, you are not going to answer this?
No, sir. I was about to ask something.
Ask.
Sir, but it's fine, sir. It's not related. I got it, sir.
Okay. But can you tell what is this approach? The name of this approach?
सिग्मा इज इक्वल टू सिग्मा प्लस अंडर रूट के लिए कोई इक्वेशन बोल रहे हैं
And I don't remember the name, sir.
It's Newton-Raphson method. You haven't heard of it? तुम लोग मैथ नहीं पढ़ते हो?
पढ़ते हैं
अलग से?
नहीं
कोर्स में नहीं है मैथ? नहीं है?
खत्म हो गया
Well, these things are getting recorded, so I didn't say it. Okay.
सर
Yeah?
what is the minimum like distance to feel the contact?
Those are contact mechanics problems. So if we start dealing with that, that's a very complicated mechanics.
Like we fix a particular distance.
You can define a zone
Okay.
and you can change it in commercial packages, but what is the question? Tell.
Like sir, like if I'm pressing like this, so there must be a minimum contact, minimum distance. After that, my fingers will feel the force. So what is that minimum distance at that point?
Yeah, that you can define. It depends on you, how approximate you want to make it. But it is not nothing to do with the atomic distance. We are not doing in that scale. If you are getting confused with that. So finite element modeling will not work in atomic scales, also not work in dislocation scales. Okay, so those things you cannot model because there it's not simple F is equal to KU. It's not that you apply a force and Newtonian mechanics works. At those scales there are different phenomena. So there are Coulombic forces, okay, and then there are van der Waals forces. So you have to take in account of all those equations which can happen between two atoms if you are modeling really the atomic thing. So when an atom comes closer to an atom and then there is a contact force, that is not going to get modeled here. Okay. So on a macroscopic scale, how a force is applied based on a surface which is in contact with another surface, so you have a friction coefficient. Okay, that is macroscopic Newtonian mechanics for friction. You have a friction coefficient and you have a normal force, and based on that your frictions are defined. Okay, so one way of doing this is to approximate a tangent, then go to another point, approximate another tangent, go to another point, and in all those algorithms, so I'm going from 0 to A, then I'm going from A to B, then I'm going from B to the exact point C. Okay, so I'm taking 3 steps from O to A, then A to B, and then B to C, and then I arrive at the correct solution, and that is happening for one point on this curve. One point on this curve. Okay, I have to follow all the points. So then the next point will begin there. So I will again make an approximation and go there. Then I will again make an approximation, go there. So at every point there will be a convergence. Okay, and you can also define that you really don't need to be exactly. So how exactly can you get the solution? So you can define the tolerance. So if the real solution, which you don't have really, but we'll discuss that, if that is, let us say, smaller than 10 to the power minus 6, you should be okay. 10 to the power minus 3, you should be okay. If the error is smaller than that, you don't really need to go any further from that approximation. So 3 approximation, you arrive at the correct solution. In these 3 approximations, you are making 3 stiffness matrices. Okay, so 3 times you are approximating. Right? This is happening not for one element. This is happening for thousands and 10,000 and millions of elements. Depends what model you have. Okay? So even if it has, so let us say you have 10,000 elements and you have 3 degrees of freedom. So you are going to have a very big matrix. Right? And you have to invert that. So stiffness matrix, you have to invert it, right? So if you have n number of nodes, 2 times of that, so 2n cross 2n will be the order of the stiffness matrix. Okay, and then you need to invert it. So that is going to take a lot of computer resources. So a lot of RAM is going to be consumed. So that is a heavy problem to solve. Okay, so what could be the other way? The other way is, don't really change the first approximation. Just keep on minimizing the error. So you take the first approximation, arrive at this point, then don't take another approximation here. Just use the previous stiffness matrix and then calculate delta U again. Obviously there will be some error, but it will be lesser than the previous one. Okay? Because with this approximation you will arrive somewhere here, right? Then you take again this slope, and so then I will make it bigger. So you took, let us say, this approximation, you went here. Okay? Now you take parallelly to this. So again you are going to come back closer to your solution. So the error is going to decrease. It will decrease faster if you keep on updating your stiffness matrix at every approximation, and it will be slower if you don't do it. But consumption of computer resources will be less in this case, and it will be more in this case, because on one point you might have to do the iteration for 10 number of times, 100 number of times, 2 number of times. That is happening at one point. So what I am trying to say is, let us say that I am going to model a tensile specimen. Okay, and so this part is constrained, and I have applied forces, and then I have some nodes. So those forces are applied on that node, so it is distributed. Okay, So this is the problem which I am going to solve, and then instead of force, let us say I am applying some displacement. I am stretching it by 5 millimeter, and then I ask my model to do it in 100 number of steps. Okay, because I just don't need the final point, I want to know the behavior. Okay, so this divided by 100, assuming that it equally divides each interval, so then you will have 0.05 millimeter of stretch in each calculation. Okay, so first calculation you are stretching by 0.05 millimeter, and so you apply a displacement of delta u, and then from delta u you calculate the amount of delta epsilon which you will have with the same functions Jacobian and all those. Okay, from that delta epsilon you will calculate delta sigma. Okay, and then you will see if you had any initial stress value plus delta sigma. If that is lower than yield strength, then it is going to be elastic only, right? So then you will tell your program to do the delta u further while updating the stresses and strain based on elastic formulation. Okay, so whatever you have calculated from elastic theory is going to be valid because stress is smaller than yield strength. So you don't really need to change your strain values, you don't really need to change your stress values. So keep that, write it down in the output file, and then ask for the another increment. Okay, so from 0.05 now you are going to 0.1, and in that case again you calculate delta u, delta epsilon, delta sigma, then you add it, and then you find out that it is greater than yield strength. So now you will have to change the calculation. Your calculation of strain is now wrong because now you are falling somewhere beyond yield strength. Okay, so before this you had all those linear calculations of stress and strain. Okay, so strain calculation is not going to be wrong, strain calculation is going to be correct, but the stress from strain, that calculation must be changing now. Okay, because you cannot do it based on the initial D matrix. Okay, so then you will have to break the strain into two parts. So whatever delta epsilon you have got, that must be broken into elastic part and plastic part. Okay, and then delta epsilon elastic will be coming from whatever delta sigma you can calculate from this divided by the elastic modulus, not really this is uniaxial. Okay, and this must be following, so let us say d sigma is following some slope with the plastic strain. Why am I writing HP? Okay, and then you have a total slope, so d sigma will also be equal to the total modulus into the total strain. Okay, so this will be elastic plus d epsilon plastic, and that will be equal, so this part I know is going to follow this kind of rule. So I will have d sigma divided by elastic modulus plus d sigma divided by plastic slope. Okay, so then I have d sigma on this side, d sigma on that side, so that will get cancelled out. So 1 by Et, should I have Et? Yes, Et I have here. So 1 by Et is equal to 1 by E plus 1 by Et. Okay, and then there has to be some method of calculating the slope in the plastic region. So you have to define in the model the behavior of, so stress strain behavior of plastic deformation also. If that information is not there, finite element method is not going to tell you how material is going to deform. It can just calculate for a component. So it's similar to elastic calculation. If you don't give the Young's modulus value, FEM is not going to tell you what is the value of elastic modulus. It is going to tell you if you apply certain force, how much displacement will come, how the things will deform locally, and all those things. It is not going to give you a value which is not there. The material property is not going to come from FEM. Okay? So the plasticity you can define. So when we model this, either by writing your own code or by using a commercial finite element package, you need to define your material. So when you define your material, you define the elastic behavior. Okay? When you define your elastic behavior, you can have different types of elastic behavior to define. Okay? So very simple elastic behavior is linear elasticity, which is isotropic. And for that you need two constant values, which is Young's modulus and Poisson's ratio. If it is going to be anisotropic or orthorhombic, or it is going to be different elastic modulus for different temperatures, all those things are possible to model. But you need to inform by giving that data. So for example, you can make these things as a function of temperature, and in that case you will have to provide the data for every temperature you want to model. You can also couple the effect of temperature with the calculation of displacement in an easy way. Is that where you are not really solving heat transfer equations, you are just solving for displacements of, so solving F is equal to KU equation, but temperature information is only used for calculating strain, thermal strain. Okay, so there is no calculation going on in calculation of stresses and all those things which are dependent on temperature. There is no real solution for temperature at every node, but there will be an extra strain which will be calculated by coefficient of thermal expansion and delta T, and that amount will be added to the amount of strain which you are calculating from displacement. So in this part will be just added, and you will have a different value of strain, and for that the stresses will be calculated. Okay. When you go to plasticity, then you have to define yield strength. Okay. And here you have to, because you have already defined elasticity, so you are not supposed to give total strain here, because elastic strains will be calculated. So you are supposed to give only plastic strain. And how can you get only plastic strain versus stress? From a stress strain diagram. So again, on the same problem, I am going to model that tensile testing of a steel. Okay, and for that steel, I have a stress strain data which has come from performing an experiment in lab, and this is the stress strain behavior, and this is my yield point and all other points, you know. So I know the elastic modulus of this material, Poisson's ratio of this material. How do I describe, or how do I get the stress versus plastic strain? Because that information I have to provide to the model. So how do I get it?
Experiment.
हाँ, ये रहा experiment का result.
We used it.
इलास्टिक लिमिट के बाद से
इलास्टिक लिमिट के पूरा सेंटेंस खोलो.
इलास्टिक लिमिट के बाद से स्लोप लेंगे तो वो स्ट्रेस वर्सेस प्लास्टिक स्ट्रेन आ जाएगा.
कहाँ पे स्लोप लेंगे? स्लोप is continuously changing, and at UTS it becomes 0. हाँ? Very good. कैसे निकालेंगे इलास्टिक स्ट्रेन? हाँ? कैसे निकालेंगे, क्यों निकालेंगे वो नहीं पूछ रहा हूँ, कैसे निकालेंगे? From total strain, how will I subtract the elastic strain? In calculation, I have data, no? I have stress data, strain data. So I have 200 is the yield strength, and there I have 0.002. Then I have 250 something, 300 something. Now, so this is total strain, right? This is the strain from there. This is the stress. So how do I get the plastic strain only?
Minus elastic strain, like linear. We took a linear function before as elastic.
हाँ, बोलो मेरे को value बोलो. What will be the value of plastic strain? क्या लिखूँ यहाँ पे? बोलो. Yes. This will be Et minus sigma by E. I have sigma and I know E. पूरा एक कोर्स पढ़ा. So this you will have to calculate, and this information you have to give to the model. When you provide the information in this form, then as I told you, this algorithm, so what will happen? The stress will be looked for whether or not it has crossed yielding or not. If it has crossed yielding, then we have to do plastic calculation. For plastic calculation, we have the amount of d epsilon. From that d epsilon, delta epsilon, I will be calculating equivalent plastic strain. Okay, what is equivalent plastic strain? It is similar to equivalent stress, which is von Mises. Similarly, you have equivalent plastic strain. Okay, you will be calculating increment in equivalent plastic strain. Okay, so d epsilon plastic equivalent. This you will be, so when I say delta epsilon, that is not one value. That delta epsilon 11, delta epsilon 22, delta epsilon 33, 13, 23, and all those things are there. It's a tensor. Okay, so from all those values, you have to calculate a deviatoric part or dilatation part of strain. That is this. Okay, and now what will you do from this? So from that you will be calculating, so you will be dissociating that into elastic and plastic part. Okay, so this is total. So from all the components you will be subtracting the elastic part. Whatever will remain will form the plastic strain increment tensor. Okay, and from that you will calculate this equivalent plastic strain increment. From this equivalent plastic strain increment, now I have to find out what should be the stress for this much increment of strain. Okay, yielding कैसे पता करते हैं? Yielding पता करते हैं von Mises criteria से या Tresca criteria से. Okay, so we don't really say that when sigma 22 is greater than sigma naught, then it is yielding. No. So one of the component might be greater than yield strength, but that doesn't mean it is yielding. Von Mises or equivalent stress has to be greater than sigma y. So it is not that, it is equivalent stress. Okay. So this relation, which is coming from uniaxial test which you are doing in lab, is reciprocated in the model in the form of equivalent stress and strain. Equivalent stress and equivalent plastic strain. Okay. So for this much amount of increment in plastic strain, what should be the new stress value? Okay. So how this model will do it? You have provided a table, so it will look that where the total plastic strain, you also had initial plastic strain. Okay. So you must have delta, so epsilon plastic. So the new epsilon plastic in ith iteration will be epsilon plastic I minus 1 plus d epsilon plastic equivalent, right? And for this value, now it will look in the table where this value falls. Okay, so if the value is somewhere here, so let us take that this value is epsilon plastic, and the value which you are getting is 0.0025. Okay, so this falls somewhere in between these 2 points. Now what will it do? How it will calculate stress? Linear interpolation. Now y2 minus y1 by x2 minus x1 is equal to that. So that's how you get EP. Where is EP? This one. So EP is different between the points which you are giving. Okay? कुछ समझ में आ रहा है कि नहीं? नहीं समझ में आ रहा है? बोलो? सच बोल रहे हो? बाकी कोई कुछ नहीं बोल रहा है. Okay, so because you guys are IT guys now, what can I do? So let us look at a code. Okay. So where are we? Not correct. This should be for isotope. This is the code for isotope, but this is isothermal elasticity. I don't want isothermal elasticity. Kinematic hardening plasticity. इसके बाद isotopic. Okay. So initially you have elasticity, lambda is linear constant, mu is shear modulus. So these are the equations for calculation of increment in stress. Okay. So don't really have to bother there. But here what is happening is this is your von Mises stress. Okay. This is von Mises minus sigma y, which is coming from the material property. If that is equal to 0, then you are on the yield surface. Okay. So this is the thing which I explained in this curve will be happening. So suppose for this much amount of strain, this is the strain which you get, equivalent plastic strain. For this much amount of strain, now from this table, because you really don't have that point there, you will have to calculate a stress value. And how will you say that that stress value is the true value? So you will have to do that. Okay, so you'll have to converge so that this difference comes very close to 0. So 10 to the power minus 6 or so. If that is done, then your plastic calculation has converged. Okay, and then you can move on. Yeah. So and then here root over 2 by 3 epsilon PL ij inner product of two tensors, that is your equivalent plastic strain calculation. And forget about these because we don't like these things. So now let us come to the code. Okay. So what is happening here? You guys should be able to understand this better than me. So you tell me what is happening here.
Sorry, language कौन सी है?
Hebrew. ये ऐसी बूढ़ी लैंग्वेज है जो तुम लोगों का सुना भी नहीं होगा. ऐसा नहीं, ये पोर्ट्रान है. नहीं सुना है? पोर्ट्रान नहीं सुना है? क्या हो गया तुम्हें? Everyone has shifted to Python.
Yes sir.
Very good. So but it doesn't matter. So well, NDI is direct stress value. So the number of direct stress value you have. So you have 3 direct stress values: sigma 11, sigma 22, sigma 33. Okay. And NSHR will be N shear. So here what is happening is this is the slope of delta sigma. So this is that. Okay. So it doesn't matter. It's the elastic calculation which is going on here. Okay. So you have E lam is Laney's constant. Okay. And then you don't do it in one instance, you do it in 2 instances, and you calculate what should be delta sigma by delta epsilon that slope. And from that you update the elastic strain value. So this will be happening only for elastic part. Okay. So here is what you are doing. So your stress values are the previous stress value plus the slope into ds tran is the delta increment in strain. Okay. And then you are calculating von Mises here. S Mises is equal to sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square and blah and blah and blah plus 2 into or 6 into shear stresses. Okay. So that 6 into stress K1 square is happening in the next step. Okay. So von Mises is calculated. So now von Mises is equal to square root of S Mises by 2. So this S Mises, it is just changing the variable name. Okay. So in each line, so the calculation of von Mises is broken into these 3 steps. Okay. ये सब मुझे लगा इतना मेरे को पता ही आगे चलो. ये सब तो मैं समझता हूँ. Now for calculation of the slope between stress and strain, there is another subroutine which is being called here. Okay, so U hard is the subroutine. Whenever there is a plastic deformation happening, it will call this subroutine, and in that subroutine, the calculation of new stresses will be happening. So the slope of hardening EP will be calculated by that subroutine. Okay, and then here is your, so if von Mises is greater than 1 plus tolerance, and this tolerance is the value, so like 10 to the power minus 6. So you can't really make it 0. Numerical 0 is impossible. Okay, so in computer course you don't really get 0. At some decimal point it will have some value. Okay, so you need to fix it. Otherwise वो फंस जाएगा program उधर. So S yield 0 is the previous yield. Okay, so बेटा so suppose this is the previous, यहाँ पे convergence हुआ है. Now the stress has gone beyond, so the strains are such that stresses are higher than 200. So that is going to be your new yield strength, and you see that between each point you have, the slope will be different, right? So when you have this stress strain diagram and then you subtract all the elastic part from it, what will happen? That this curve will shift on this side. You are subtracting the strain. Okay, so your new curve for will be looking like this. So this point, well, I have not drawn correctly, so this point is shifted here. So this will be yield point. Do you follow? You can do it.
Yes.
It's very simple. So between this point and this point, you have this slope. This point, you have a different slope here. Guess how I was thinking. So in every 2 points, you need to calculate the new slope. Okay? And then after that, at the end, you calculate your epsilon plastic and you converge it. Once the convergence is done, then you update the new stress before the convergence is done. So if you have not, so for your 0.0025, if you have not arrived at the correct stress, then you cannot conclude that your stress strains are fine. Once that is done, so it has converged. So 1 plus tolerance is now equal to 0. In that case, you will be updating your stresses to the newer values in the ith iteration. Okay, and then you will apply the next delta U. This is how plastic calculation will be done. Okay? Okay then, done.